Let's get started. This is probably the second last recitation, so there will be another recitation next Thursday. It's the final review, so please, if you don't have other things, please come to the final review. And hopefully Manzil will do a very broad review on what the topics we cover after the midterm. So today I'm going to go over deep networks and basically working on some really fundamental things that's probably going to show up in the final. And but before that, a bit administrative stuff on the project presentation. So if you go to AutoLab, and here's a link on the presentation, and you can see 4 links here. And then you can click on group options, and then you can enter your partner's email. And you can form groups on AutoLab. And if you submit only one copy, the AutoLab will automatically submit copies for all your teammates, so you don't have to do the actual work. You have to sign up for the presentation by tonight. Tomorrow I will send out Dropbox links for each group, and so you can upload your slides to the Dropbox as well. Submit one copy to AutoLab, another copy to Dropbox. You can keep modifying your copy on Dropbox before the class, and then but the AutoLab is due on Sunday noon, so you can simply submit a draft on AutoLab. You simply need an entry to grade your presentation. Otherwise, we don't have ways to keep the feedback and scores. Okay. So that's all about the presentation. Yeah, you only have 5 minutes for presentation. We keep emphasizing on this because we have 30 groups. So for 2 classes, basically each class we will have 15 groups. We're under pretty very limited time constraints, so please practice before you present and make sure that you have very good time control. For the final report, there will be a more detailed description on the site, hopefully by the end of this week. Basically, you will work out a report with a page limit of 8. So you can submit like a 4-page report or a 6-page report, but definitely no more than 8 pages. Otherwise, since someone will read that and give you a grade, and keep it short. Okay. So, yeah.
For the report, are we supposed to still follow the ACM?
Yeah. You have to submit a paper.
How many pages?
Upper limit is 8. So you can submit like 6 pages or 4 pages, that's fine. But no more than 8 pages. Okay, so today we're going to cover deep networks. This is a topic that we don't have any homeworks, but it's going to be in the final exam. There will be a very pretty simple question on this topic, and I'll cover some of the contents in today's recitation. So if you read New York Times or some magazines, you'll find out some reports saying that the computer really understands what people are like. What is the image? What are all the features, or what are all the objects on the image? Well, actually, that's not true. Some people claim that deep networks understands like images and text. That's actually some statistical model that something like maximize the likelihood of the data, just like all other models. So there's no magic in deep networks. The advantage of deep networks is that it's actually a very strong model to soak a huge amount of data. So if you have like terabytes or petabytes of data, something like kernel methods will fail. Remember that when we compute kernel matrix, it's going to be n times n is your data points. Now you have terabytes of data points, and that's actually not a feasible way to apply those methods. So, but deep networks is kind of scalable, and it has very parallel structure, so you can it's very easily to implement it on a distributed system. That's why now deep networks are very popular. And yeah, so here are some networks. So there are two types of networks. One is called neural networks. The other one is called belief networks. So you may have heard of convolutional networks or recurrent networks. That's all belong to neural networks. For belief networks, it's actually some work brought by Hinton in 2006. And those stuff are RBM-style networks. When you train those networks, you have to use something like a very completely different approach than stochastic gradient descent. The training algorithm is called contrast divergence, which is an application of Gibbs sampling. And actually, those models are very hard to train and very hard to use. It does not have a very significant better result than neural networks. So I think belief networks has its own theoretical value, but in practice, especially in industry, people use neural networks more. And yeah, if you look at Andrew Ng's recent AMA, he actually addressed this problem that belief networks are less practical. So today I'm not going to cover belief networks. It is out of scope. So if you want to know belief networks, you can take Hinton's online class or take deep learning class next semester, taught by Big Shang. And so we can look at several types of neural networks. So back in like 30 years or 20 years, people refer to one-layer neural network as logistic regression and perceptron algorithm. So you can see that as a very shallow structure, only two layers. Right? For multi-layer perceptron, we often think that as a network with hidden units. So if you add hidden units into a network, actually you add a nonlinearity upon a nonlinearity, so that which creates non-convex functions. So the hidden layers actually making the entire model to be non-convex. When you do the optimization, you actually end up with some local minimum. And yeah, it's very hard to verify if your local minimum is a global minimum. For deep networks, as I mentioned, there are two types of deep networks. Two most popular type. So the first one is convolutional networks, CNN. You may have heard of the net or ImageNet before. The net is a network developed by Yann LeCun in 1990s, or around that time. That's a network for digit recognition, handwritten digit recognition. ImageNet is actually for image data set that has like 1,000 classes. Memory-based neural networks, for example, recurrent neural networks, which adding a memory into the neural network. I will not go over that today. If you have interest in that, you can. The best paper might be Nikolov's thesis and Alex Griff's tutorial. So you can go over that. So here are some key concepts in neural networks. The training algorithm is backpropagation, SGD. So backpropagation is essentially SGD. Basically, you calculate the gradient and do the gradient descent. That's it. Nothing really special, and that's probably, the matrix calculus is probably the only math that you need in solving a deep network problem. So nonlinearity is so deep networks is a non-convex problem, and basically adds nonlinearity upon a nonlinearity. And there's actually a paper proving that even for a neural network with only one hidden layer, it's a universal approximator of any function, any borrow measurable functions. So for a borrow measurable function, it contains all the continuous function and most of the discrete functions. So if you have a neural network with only one hidden layer, with nonlinear activations, it is able to approximate any functions. So the problem is that I just claimed that there's one hidden layer, but actually you may need a lot of neurons, like 1 billion or 1 million units, to approximate a very complicated function. So that's the reason why we're going deep. If we have a deep structure, for example, if you have like 5 hidden layers or 6 hidden layers, the top hidden layers will be exponentially powerful than the lower layers. There's actually a paper proving that, because you have nonlinearities on nonlinearities, so the neurons getting more and more powerful. The vanishing gradient problem, as you may see that, do we have a chart? So if you go to the lecture or you watch the Alex lecture video, or hopefully he posts that. So you may see that we often use 10H or sigmoid function as the activation function. So I think everybody knows 10H. So sigmoid is basically a function that with this shape. So it approaches 1 when it goes to positive infinity, and then it approaches to 0 when it goes to negative infinity, and 0.5 here. So this is a typical nonlinear activation function. It's also called a squashing function. Why we need such a function in the neural networks? Because the hidden variables may be very large or very small. So a squashing function is taking any kind of input and then squash it into 0 and 1. So basically you don't have very large numbers in the network, which may cause it unstable. But the problem is that these kind of squashing functions will have very small gradients on both ends. So if you go very deep, you do the chain rule back, and then you may end up multiplying very small numbers. And then this can be extremely small when you have like 5 or 6 layers. And so let's say this is a network, and this is a input. So the vanishing gradient problem is that when you do the gradient descent, the gradients right here will be very large, but the gradients right here will be very small. That's because of the chain rule. So if you have a very small number and then you multiply them up, the gradients here will be very small. So actually, at the end of the training, the weights right here will be like pretty much like random numbers, and here will be like a trained weights. So, but actually the weights at the bottom are more important than the weights on the top, because the weights right here basically shapes the entire network. So that's the vanishing gradient problem. Actually, deep learning model is invented like 30 years ago, but people don't have a way to get rid of this problem. So that's why it takes so many years to find some way to practical ways to get rid of this problem. Yeah. If you're interested, you can look for a paper that's by Yosha and Zhou. It's actually a milestone paper talking about the vanishing gradient problem. So the content addressable memory is is the belief network stuff, so I'm gonna skip that. There are several techniques to work on generalization, like dropout or early stopping, or yeah, probably other like momentum or weight decay. There are a lot of small tricks on training a neural network. So basically, people find that if you apply a small trick on the neural network, your accuracy goes up like 1% or 2%. And then you apply another trick, it goes by like 1% or 2%. If you apply a lot of tricks, and fortunately all those tricks works, you'll end up with a pretty significant difference. Constraints. So you can actually add in some interesting constraints on any variables in the network. You can add sparsity constraints. For example, so let's say this is a network. You can add sparsity constraints on this network. You can either add sparsity on the activations, which are the hidden neurons, or or you add sparsity constraints on the weights. If you add sparsity on the constraints on the weights, most of the weights will be 0. So that actually forces your network to learn local features, just like convolutional networks. You'll see that in a minute. Actually, that's actually the advantage of not having a fully connected layer. You have less connections, you have less parameters, and then you can learn from local. For sparsity on the activations, that's actually is somehow similar to dropout, but with different approaches. If you shut down some neurons, you can have other neurons to learn more powerful features. For example, if your original neurons learns like eyes or noses or mustache, if you shut down some neurons, other neurons might learn some more high-level features like faces or like body. So actually the sparsity enforces other neurons to learn more complicated features to get rid of overfitting. Let's go over the backpropagation. Oops. Forward propagation and backpropagation. So suppose we have a fully connected neural net. How do we compute the output? Right. So let me write this one. Let me write in matrix form. So let's say this is X, and here are the weights. X are the input neurons, is a vector. WIH is the weights from input layer to hidden layer. H is the hidden layer, and WHO is the hidden layer, the weights from hidden layer to output layer. Y is the output. So suppose we include a bias into X, and then we somehow incorporate the bias into H. So I don't explicitly write a bias just for convenience, but in practice you have to add the bias into that. So H is simply F WIH times X. Let's suppose X is a vector. Let's say the dimension is F times 1. And WIH has a dimension of H times F. Basically, for each hidden neuron, it has like F weights to each of the X, and then basically the weighted sum to get the value for the neuron. Right. So I'll write another structure. Let's say this is a neuron in the layer, and then you have x1, x2, and probably this is bias. So this is the weight, let's say 1, 2, this is 0. What you do is simply H is simply a sum of elements. That's it. So here is a weighted sum, and F is your nonlinearity. So you can have like 10H or RELU or other squashing functions. Okay. So from H to Y is exactly the same procedure. Basically, you do that again to get Y. Any problems? Yeah.
So you're just iterating, weighting, transforming, weighting, transforming, weighting, transforming?
Yeah, so basically from one layer to the next layer, you basically do a weighted sum and then do a nonlinearity on each of the elements. Element-wise nonlinearity, and then do the same thing again. This is a forward propagation.
So in the forward propagation, the weights are given. The weights.
Yes.
Weights.
You use the current weights. So the weights are initialized randomly, and then you use in the forward propagation, you use the weights to compute the output. In the back propagation, you calculate the gradient on the weights and to update that. Okay.
Which should be scalar or vector?
Weights. Basically, each link corresponding to a number, to a scalar. If you get everything together, it's going to be a matrix. Right. So here, weights are a matrix. It's H times F matrix.
The nonlinear function you use, is it always between 0 and 1? Or
No.
can we make this variable?
You can use any nonlinear function, as long as it's not linear. You should
In between nodes, is it once we select some function, we always stick to it, or we can have scaled version of it?
Basically, you can pick any nonlinear function you like. As long as it's monotonic, I think that it will be fine. And you can use 10H, right? 10H is from -1 to 1.
But I mean, once we select one, do we apply it to every node, or can we have variation?
But from one layer to usually from one layer to the next layer, you will have you apply the same nonlinearity.
Okay.
But from this layer to this layer, you can use another one.
Is there an intuition behind like what kind of function does what things? Like which one do we use?
Well, for hyperbolic tangent with sigmoid, you can. I mean, they are basically the same. You can choose one from the other. But I'll show you, like in a minute, some other functions may have some better properties that you may want to use them in some occasions.
What properties are we looking for?
Basically, some functions like rel, Alex talked about in class, with this kind of property is actually a max function. So in this case, the gradients, if it's greater than 0, the gradients are fixed. So you can somehow alleviate the vanishing gradient problem. That's why this function is better than sigma, in some sense. But this activation has its own problem. We'll talk about it later. Any other questions on the forward propagation? Make sure that you understand this. Okay. You can write down a very simple network and then using some very simple numbers to
The loss
do
function
this.
for every layer must be the same.
Loss function for what?
Every layer.
No, you don't have. You only have loss function on the top. So basically, when you compute y, you will have a target y. Right. If you do a regression problem, you may have real value vectors. If it's a classification problem, if it's a 1 over n, 1 over k classes, you will have something like a, well, in NLP, people call that one hot vector. Basically, you have a 0 vector except for one entry that is 1. In other, like, it has a lot of names, basically, saying the same thing. Canonical vector, something like that. Yeah, any other problems? I can go very slow, but just make sure that you understand everything, okay? So here are some loss functions like L2 loss. If you do a regression problem, you probably want a L2 loss. If you do like this problem, you probably want a cross entropy loss. That's a better way to do classification. Yeah.
The loss is to get the weights.
The loss is actually a measure on how your current model deviates from your target value. And then you can compute the gradient, and then you do the backpropagation.
But I mean, you bring the loss function in order to find weights, right?
Yeah, yeah. Okay, no problem. The backpropagation. So as you can see, that backpropagation is actually the chain rule, right? It's exactly the chain. So you have the loss function with partial loss, partial y, is the derivative with for loss with respect to y. Loss is usually a scalar, and y is a vector. So this ends up with a vector. And all other terms except the first term is going to be a matrix. And then you have matrix times matrix times matrix times the vector. It's a vector. And then the first term is going to be a tensor. But if you go to the class, you will know this is a tensor. Or if you want to get rid of tensor, you can. There are two approaches. So basically, you can do the derivative with respect to each row or each column, or you can somehow convert the first tensor, because the first tensor is a diagonal tensor, and you can. Is equivalent to, let me write that down. So the first term is something like you have all zeros elsewhere in this tensor, but on the diagonal you have a value of x. So basically, each element on the diagonal, each vector on the diagonal is a vector of x. If you don't want to go over the matrix calculus, you can actually do element by element. Right? If you implement that in like MATLAB or Python, you probably want to do a matrix calculus. But if you do that in exam, you can actually do element-wise gradient calculation. For example, if you have a network, let's say this is y1, this is y2, and this is a hidden. Okay, so this is a network with a very funky shape. I just use that for explanation, but I haven't seen a network with a size like this before. So when you calculate the gradient, you first have to calculate the loss function with respect to y, right? And then you calculate the y1 with the derivative of y1 with respect to h, and then you calculate the gradient here. Let's say this is w. And basically, you do partial loss, partial y1 times partial h, and then this partial loss This is how you calculate the gradient with respect to W. Basically, there are two paths, right? You have to compute the gradient on each branch, and then sum that up and do the final step. Hopefully this is clear to you. This is not too hard, right? It's just how you compute the gradient.
It may be a basic question, but why the last term is not partial H or partial X?
Partial.
The last term. Yeah.
Oh, here, right. H is actually W times X. Right? So partial H over partial W is actually, you can write as partial H, partial F, partial W. You can do this. And from Y to H is the same thing. Okay, hopefully you're comfortable with this. Yeah.
So you said the tensor only has a diagonal component.
Yeah.
Is this the case for any derivative of a vector with respect to a measure?
No. Let me think about it.
And why is it the case?
Because if you have, let's say you have x equals to alpha x, right? So let's say this is a vector and this is also a vector. Here is a matrix, and when you do partial y, partial w, you end up with a diagonal tensor. That's because your y has this form. But if you have an arbitrary function, like this one, sorry, this won't be only the diagonal. Any other problems? Okay, you can just go over the entire process on the paper. Like work out a very simple case. You understand that.
Do you have like a simple example that we could like around? Actually, numerical example.
You can just draw a simple network and like assign 1 or 0, and then you can work that out. It's very simple, and you can use MATLAB to check if you get the right answer. It's very, it's pretty simple. Okay. So Alex actually write the matrix calculus in a slightly different form. If you look at the lecture video, that's basically he used a different layout for matrix calculus. There are actually two layouts for matrix. One is called the numerator layout. That's what Alex uses. This one is called the denominator layout. The difference is basically, it's just flipping rows and columns. That's it. So if you see a different form, don't get surprised. Momentum is actually a small trick that you can apply to get rid of local minimum. But you cannot guarantee that you can get to a global optimum. Even if you get to a global optimum, you have no way to verify that in the general case. So momentum works as follows. If your error function looks like this, okay. You can see here is a very small bump. If you do the gradient descent, if you luckily or unluckily get to here, the gradient will be 0. and the SGE will stop. Right? The gradient descent will stop. If you have a momentum, actually that's actually adding some constant times the last gradient. So basically, when you do this and this, if you have a momentum, you kind of need to go like further with this momentum, because you're adding a fraction of the last change that you made. Right? And that actually helps you get rid of this local mole. That's the intuition behind the momentum. It's a small trick in training. But if you have a very large valley, and somehow get stuck into that, you'll probably just stay there. Another thing, okay.
How hard is it to find like a good eta for this trick?
I think there might be some papers like, I'm not sure. I know there's something called eta grade for the learning rate, but for the momentum, I don't know if there are research on momentum. Yeah, people use something like 0.1. I don't know if there's a reason for that, but I mean, you'll find a lot of magic numbers in the ImageNet. So even in the very early papers like the nets, they have very magic mappings, and nobody knows why. Okay, so here's the ImageNet. So ImageNet is actually a neural net that built on a very large data set. So I remember it has like 1,000 classes, and after the last layer of the network is actually a softmax layer. A softmax is it's also called a multi-class logistic regression. So basically, your output is a vector, consists of probabilities that sums up to 1. So you can pick the highest probability as your class label, or you can pick k highest labels as your classification result, and you see that if your true label falls in that k predictions. Okay. So here are top 5. Yeah. As you can see, that usually it does pretty well. Even it makes some mistakes. That's very reasonable mistakes. If you're interested, you can read that paper. Oops. Okay. So I think Alex covered convolutional networks in class. I'm gonna elaborate a little bit more, on how convolutional and pooling layer works. So there are 3 types of layers in convolutional networks. One is called convolution layer, one is called pooling layer. The other one is the fully connected layer that we see before. Convolutional layer is built based on intuition that it's like a filter that scans the entire image. While you scan the entire image, the filter is fixed. So, yeah, suppose everyone knows what is a filter. That's actually a technique in image processing. If you want to detect a line, you can actually have filters like this. So if you have a line, let's say if you have something like this pattern in your image, I'm going to do a dot product, element-wise product on these two, and you'll get a very high value. If you have something that is not a line, like a column, but the value will be lower. Right? It's very true. The convolutional layer is like you have a filter that scans through the entire image. The weights for the filter are fixed. So basically, for it's a 3 times 3. layer, 3x3 filter is also called a kernel. So you have this filter scans through the entire image, and the output is the element-wise product with some nonlinearities. Basically, you do a weighted sum in the kernel, and then you apply some nonlinear functions to the to here, to this block. As you can see, this is a line detector. If you have a line, actually the output will be fired. Will have a very high value. We say that is fired. If you move that one block to the right, it will have less. It will have less value because it's actually a corner. So if you have very proper threshold, you can have a filter that only detects lines. In terms of neural networks, it's like you have a fixed set of weights connects to. You have sparse connections with fixed weights, because each neuron in the next layer is only connected to a few neurons in the previous layer. That's the intuition behind the convolution. Okay, everybody's fine with that, right? For pooling layer is a very simple operation. Basically, with the entire with all the neurons, you do something like a local maximum or local mean. You can have like a 2x2 or any arbitrary size block, scan through the entire 2D layer, and then you can do the mean or the max with each block. That's the value for the next layer. That's the pooling layer. Okay. So this is the network architecture for the ImageNet. As you can see, they pump in like 224 images, 224 pixel images, and then they do they feed that into the convolutional layer, and it come up with two branches. So the top branch is actually a model, and the bottom branch is actually another model with exactly the same configuration, but they have different initializations. So at the end, they do a model averaging to compute the results. If you see something like multi-column deep networks, it's actually averaging on 25 networks. It's the same intuition here. Okay. The paper claims that they use ReLU activation. As I said, the advantage of this activation is the gradients are fixed if you are greater than 0. It's just like whatever it is, and you can use the soft flux function to get rid of the non-differentiable point. But actually, in practice, if you just use this that max function, it's fine. Because you always have fixed gradients. I mean, the scale is always pretty large, and you can have very fast convergence. That allows you to train on very big data. That's the advantage of this activation. But the drawbacks is that you simply throw away the entire negative part. So Alex actually talked about a modified version of this ReLU is something like this. So this is still a nonlinear function, but you have like very small slope right here. It's called leaky ReLU, but I think it has another name when Alex teaches that. Anyway, this allows you to somehow get the gradient if you instead of the 0 gradient. ImageNet approach has some approaches for reduced overfitting. When we do all image classification or segmentation tasks, pretty much in 90% of the cases, we can flip the images to get extra data, right? So if you flip the image of a person, it's still a person, right? But that does not apply to something like digit recognition. If you flip a digit, that's not a digit anymore. So it's a very, very cheap trick on getting extra data. The second one is a little bit tricky. They use PCA for the data augmentation. What they basically do is they collect all the pixels. Each pixel has RGB values, so you can think that each pixel is some new data point that has only 3 features. And then you do a PCA on the all the pixels. Basically to capture the 3 principal components on all the pixels. And then you can multiply that by some number, by some small number, alpha. That's basically adding some noise into all the pixels in the image. So by applying that, you can have a network that is robust to noises to some extent. Dropout is also a technique that Alex covered in class. So basically, you can randomly drop some neurons in the network. During the classification time, you just use the expectation to get the classification result. Local response normalization. I don't want to go over this because it has like K, alpha, beta, N, right? It has like 4 magic numbers. So I think they somehow engineered it. So it might help, but in general, but I think too many magic numbers is not a good idea. Anyway, the last one is overlapping pooling. So originally in pooling layer, each kernel is not overlapping with each other. So, but in here they have overlapping pooling kernels, which is, I mean, it may improve the accuracy to some extent, but I don't see a lot of people using that. The data set, they use a very large data set with pretty much roughly 1,000 images in each of the 1,000 categories. They have like 1.2 million training images. And they downsample the image because they have different sizes. And then they downsample all the images into 256 times 256. And they extract images from the size they want. Yeah, here are the results. Sparse coding is actually something like component analysis. SIFT and FV is called a feature vector. It's a technique that used in CV. Probably you know better than me. They are traditional CV techniques. As you can see that their network actually performed much better than previous state of arts. Okay, that's it. Any questions?
What's the error problem?
Is it the error rate?
Yeah, error. Yeah. What's the meaning of the value, the percentage value?
Percentage, yeah. It means like the images that you wrongly classify divided by all the images. Any other questions? Yeah.
What is the problem that you mentioned with the ReLU application function?
The drawback of ReLU, right?
Yeah.
Because if you have ReLU, you actually have like the left half part to be 0. Right? You basically throw away all the gradients, if it's equal to 0. So you don't have gradients at this side. Any other questions? Okay, good luck on the presentation and the final exam.